Hello dear students, I am Dr. Moin. In this video we are going to discuss about differential scanning calorimetry DSC. Students, this is part 2. In part 1 we have discussed the introduction of DSC, then we have seen the principle of DSC, and we have seen the detailed instrumentation of DSC. So if you didn't see yet the part 1, then I'm putting the link of part 1 in the top right corner in the I button so you can watch it. And here are the contents of current video. We'll see the working of various types of DSC. We have already seen the different types of DSC in part 1, so now we'll see their working. And then we'll see the various applications of DSC in detail. So first of all, we will see the heat flux DSC. In this type, the measurement thermocouples are positioned beneath the sample and reference pans. So the sensors are beneath the sample and reference pans. Such a design of DSC may be used to measure specific heat capacities. Now, the shift in baseline is only influenced by the changes in specific heat capacity of sample. Now, what is shift in baseline? So you can see here are the DSC curves. So this one you can see here is the baseline, and this one is the smooth. And in this curve you can see the baseline, but this is not smooth. This is going to vary. So this baseline, actually this is shifted from here to here. And the reason behind it, why this baseline is shifted, that is due to change in the sample specific heat capacity. And this is not due to some other properties of sample. Another thing which, affect the baseline shifting, that is, the change in baseline is also dependent on the characteristics of pans holding the test materials, so that the apparatus has to be calibrated using known standard materials. So these things can be avoided by properly calibrating our instruments by using some standard materials. The area under the peak is directly proportional to the heat or enthalpy of reaction, which is given as delta H, enthalpy of reaction, that is equal to K into sine of integration, change in temperature into dt. And this thing, sine of integration, delta T into dt, that also gives the peak area. And this K, this is called calibration constant. And actually it converts peak area into joules. And it is a thermal factor which may vary with the change in temperature. The problems of measurement of the area under the peak, it still arise owing to the difficulty in defining an accurate baseline. So if there is shift in baseline, as I mentioned earlier, then it becomes quite difficult to measure the area under the peak, or to define properly the area of the peak. However, the DSC design does have some advantages over earlier DTA designs. And in DTA designs, we know that the thermocouples were placed within the sample. And what was the benefit of it? Although the sensitivity is greater with the thermocouples within the sample. So when we put thermocouples inside the sample, so sensitivity is increased. But another problem is with that DTA curves, and that was the baseline shift that also become greater. So this problem, it becomes quite lesser in case of DSC design. In the DSC design, the positioning of the measuring thermocouples outside the test material So it may reduce the sensitivity and overall response of the technique. Next type is power compensated DSC. In this design, the sample and reference holders are insulated from each other and have their own individual sensors and heaters. So they are heated separately. The electrical circuit operates to maintain the holders at the same temperature. Means the temperature of the both pans is kept constant, and this is all done on the expense of the power. Means more power is supplied to the sample pan. The thermal energy absorbed by the sample per unit time, that is exactly compensated by the differential electrical power delta P, which is supplied to the heaters. And measuring this power, that is equivalent to the measuring the thermal power, and thus the baseline that can be expressed as delta P, which is equal to differential D of delta Q over dt, and the peak area that gives us delta H, enthalpy of reaction directly. Now we'll see the various applications of DSC. So first of all, melting point and enthalpy of fusion of various materials. The determination of melting point may be very easily done by using simple apparatus, but the calculation of enthalpy of fusion is much more difficult. DTA can give excellent qualitative measurement of melting temperature, while for measurement of enthalpy of fusion we must have to use DSC apparatus. In this case, we get sharp melting peaks with suitable apparatus over a very wide range of temperature. For example, one of the DSC curve that is shown over here, and that is DSC peak for pure indium. So you can see, so there is a curve, endothermic process, and this temperature, this is the temperature at which this indium starts melting. So the melting point and enthalpy of fusion of these compounds, which are determined by using DSC apparatus, so these are in good agreement with the literature values. So means the values of enthalpy of fusion calculated by a DSC method, they are quite very much reliable. Next application is crystalline phase transitions. We know that crystals show various crystalline phase transitions upon heating. So here we are going to discuss about potassium nitrate. So potassium nitrate shows rather complex behavior when heated and cooled. So here are two transition curves. One is for when it is heating, when it is being heated, while other is when it is being cooled. On first heating, there is an endothermic crystal transition from form 2 to form 1, this one, and this is going to happen at about 128 degrees centigrade, and enthalpy of reaction for this one is about 5 kilojoule per mole. And then when we continue heating it, so finally we get another endothermic peak, and this shows the melting point, and it occurs at 334 degrees centigrade with enthalpy of fusion of around 10 kilojoule per mole. Now we start cooling this molten potassium nitrate. So if the sample is then cooled from about 150 degrees centigrade, so we get an exothermic peak at 120. So this is talking about this peak which is going to obtain at 120 degrees centigrade, and this is exothermic peak, and enthalpy of reaction is only 2.5 kilojoule per mole, and this is with negative sign because the peak is exothermic. This must mean that it is forming a different phase from 3. So here it is going to convert in a totally different phase. And further, at lower temperature, it transforms slowly back to form 2. So this is talking about this one. So if we cooled it further, so it is converted into form 2 here. Next one is heat capacity measurements. Now, what is heat capacity? The amount of heat needed to raise the temperature of the sample by 1 Kelvin is its heat capacity, Cp of sample, given in joules per Kelvin. That is equal to Curry heat of the sample divided by Curry temperature. On a DSC instrument, the calibrated y-axis, so we are talking about this one, y-axis, so it represents the differential rate of supply of heat energy, or we may call it change in power. Then we can see here is a DSC curve, and that is for heat capacity measurement on molten polyethylene. So our sample is polyethylene. So here we have the 3 baselines. You can see the 3 baselines. This one is for reference, that is no sample baseline. This one is for our sample, polyethylene baseline. And this baseline is for the calibration component, that is sapphire. So since we are heating at a constant rate, the product of the y-axis deflection, delta y, which can be calculated by this one, that is from the sample baseline to the no sample baseline. With no so I repeat it again, the product of the y-axis deflection delta y from the baseline with no sample, if it is divided by the heating rate dt by dt, it should give the difference in heat capacity due to sample, which is given by this relationship, where K is the calorimetric sensitivity, and it can be found by the calibration of the instrument. And generally the calibration is done by using sapphire, which is a pure crystalline alumina whose heat capacity is very well known. So next application is the transitions in various metal complexes. So we have selected here cobalt pyridinium chloride, and here is the DSC curve for this cobalt pyridinium chloride. So 3.4 milligram of sample was taken, and the temperature programming was 8 Kelvin per minute increase in temperature, and the atmosphere was flowing nitrogen. So here's the DSC curve for this complex. So it gave 4 transitions up to 500 degrees centigrade. We can see here 1, 2, 3 and 4. So first one was at about 120 degrees centigrade, you can see over here. So it was a small sharp endothermic peak with enthalpy of reaction which was calculated as 12.6 kilojoule per mole. But this corresponds to no mass loss, means during this transition there was no mass loss was recorded, and this experiment was performed in thermogravimetric experiment. Then the 3 subsequent peaks here, which were obtained at 180, 280 and 350 degrees centigrade, they showed progressive loss on the thermobalance in thermogravimetric experiment, and how much the mass was lost, that was corresponding to the loss of 1/3 and 2/3 of the total pyridine molecules respectively. And the total enthalpy of reaction for these reactions, which was calculated as 120 kilojoule per mole. Next application is the polymer cure. So curing is a process of toughening or hardening of a polymer material by cross-linking of polymer chains, which are brought about by electron beams, heat, or chemical additives. So the reaction of small molecules to produce larger molecules with different properties and more stability. Generally, these reactions are exothermic. And the average enthalpy of polymerization of unsaturated molecules like styrene and vinyl chloride that has been calculated as -100 kJ per mole. So this is exothermic. Then further, the reactions of thermosetting polymers like epoxy resins and polyesters cross-linked with styrene. These are also exothermic, and these are already studied by differential scanning calorimeter. The reaction of epoxy group with a curing agent, and normally the curing agent is amine, is the initial stage in the reaction and is followed by further reaction of the secondary amine with a further epoxy group. So here is the reaction of this curing agent with this epoxy group, and there is generated, the cross-linking, and there is the phenomena of curing of that polymer. So here is the schematic DSC curve for typical epoxy cure shown in the right. Sample was taken in 5 mg while the heating rate was 10 Kelvin per minute and the atmosphere was running nitrogen. So here are two curves, A and B. So A represent the initial run of uncured sample, mean when sample was not cured, while B is the curve for fully cured material. So this reaction occurs even at low temperature but is rapid above 100 degrees centigrade, giving the DSC trace shown on the right. The initial glass transition temperature of the starting material is followed by the large exotherm of the reaction. So we are talking about the uncured material and its glass transition temperature, and here is the exotherm. And when the material is fully cured, so sample was run again, so rerunning of the cured material show a new glass transition temperature at much high glass transition temperature at much high temperature, which is not shown in this curve. Actually it is on the further larger side of the temperature. So post curing will raise this glass transition temperature to even higher temperatures. Another application is the study of protein denaturation. Proteins may be classified as fibrous with long thread-like molecules, for example collagen, or they may be globular with compact spherical shapes such as insulin. Both types have well-developed structures involving folds, coils, or sheets, and even a helix within a helix, which is called superhelix. All of these structures are destroyed by heating or denaturation at extreme pH, and this reaction is generally endothermic, and these can be studied by DSC. So here are the DSC curves for denaturation of proteins, and these are two, A and B. So A, what is in A, actually there is 800 milligram sample, and which is actually 0.3% collagen solution, which is sealed in a vessel, and the temperature rate is 0.5 Kelvin per minute. So here you can see the DSC curve for this pure collagen solution. While B, which is looking to be a more complex one, what is inside? So it contains 850 milligram beef and fish muscle. So this curve is for beef and this one is for fish muscles. So these are again in a sealed vessel with a heating rate 0.2 Kelvin per minute. So we can see there are a large number of endothermic peaks here. There are also the endothermic peak. So figure A, this one shows the denaturation of collagen. So because here is the single material, so you get the only single peak, and this showing the denaturation of this collagen. While figure B, it shows the complex behavior, because here are the multiple components present here. So we get multiple endothermic peaks, and all showing the denaturation of proteins present in the sample. So dear students, this is all about DSC. Hope you get it. Well, so if you like the video, then like it, and if you didn't subscribe my channel yet, then subscribe it right now to get in touch with my further upcoming videos. So thanks for watching. Thank you very much.